Okay, let's see if this is working now. Uh, First time I tried this, it didn't record the audio. So my frustration, I'll try not to take out on y'all. Okay, for part C of 2.2 in Carter's thermodynamics, we're asked to find the pressure if the temperature is increased to 500 degrees Celsius. First thing off the bat, let's get rid of this Celsius. If you go over part A, in the first video, you can see how to easily uh, find kelvins from Celsius. What the heck, I'll just do it right now. We know that at negative, well, let me find a color that's not black. That would be, okay. So we know negative 273.15 Kelvin, Celsius, is equal to absolute zero, which is 0 degrees Kelvin. 0 degrees on the Kelvin scale. We add 273.15 to both sides, and that gives us 0 degrees Celsius is equal to 273.15 Kelvin. Um, in part A, we added 20 to get our temperature 1 at 20 degrees was obviously 20 more than this, 293.15 Kelvin. For 500 degrees Celsius, we add 500 to both sides. So this was our temperature 1. We're increasing it to 500 degrees Celsius. That gives us an increase to 773.15 Kelvin. Okay, so now we have the correct units in Kelvin of how we're increasing our temperature. And we want to know the pressure though. So since this is an ideal gas, we know PV equals nRT. Well, this is true for our first setup. We have a certain pressure and a certain volume at a certain temperature is equal to this constant. In other words, solving for this constant, P1 over V1 is over T1 is equal to this constant. This is also true for our final state. nR is equal to P2 over V2 over T2. And since this constant is equal to itself, we can relate this equation and this equation. So this equilibrium state at the beginning, at this temperature, is going to be equal to the final state at the new temperature. And we know that in order for this to be true, as we raise temperature 1 up to T2, one of these is going to have to go down in order to keep our constant in R. Okay, so we're solving for the final pressure. It says find the pressure. So we're trying to solve for P2 here. Well, if we rearrange this equation, we'll get P2 is equal to P1 V1 times the final temperature over T1, and V2 comes down here. Well, looking at our volume, what is our volume? Our volume from the top, V1, was 0.5 meters cubed. 0.5 meters cubed. What is our volume going to be at the end of this? So we're raising the temperature, but this was coming from, as you read it right here, it comes from a tank of volume 0.5 meters cubed. So if this is a tank, and assuming if it doesn't really expand much or explode, our V2 should be about the same. Sorry, this is a 5. My 5s look like S's sometimes. So our volume 1 and our volume 2 are identical. Our canister isn't changing, hopefully. That means we can get rid of these. That means our final pressure is going to be equal to our original pressure times the ratio of T2, our temperature, our final temperature to our initial temperature. Plugging these values in, we had 1.5 times 10 to the 6. And just do our dimensional analysis over here. That was in pascals. This temperature that we just solved for was 773.15, and that was in kelvins. And we're dividing by our was 293.15, and that was in kelvins also. So P2 is going to be in units of pascals. These cancel. So our final pressure, after plugging everything in, was definitely something. It was 3.96, I believe. 3.96 times 10 to the 6, and that was in units of pascals. So if you plug this into your calculator and get something other than this, go back and read your instruction manual on your calculator. So that is part C of 2.2. Thanks for watching.